to move the supply, we need converters, and to fix, or we can say that to make that supply more flexible to the instrument or to the electric vehicle which we are having, that we need some of the you can say that converter is the device which do the same operation what we want. And for that, so there are basically DC to DC converter, DC to AC converters, but discuss our DC to DC converter, which we also call them as a chopper circuit. Okay, so these are the chopper. Okay, so there are two type of converter. The first one is the buck converter, and the second one boost converter. So what it mean buck and boost? So buck converter basically it deals when you need to step down the output voltage with respect to the input voltage. It is called the buck converter, and that buck converter we usually say as a step down conversion of the DC to DC power. Okay, so when you just apply the DC input, okay, that is a fixed DC input, and you want to change into another DC signal. So in that case, and with the lower value, in that case we use this buck converter. The designing of this buck converter depends on the circuitry of the buck converter. In that circuitry, if you can, if you are, you will just notice here that we are having this switch, freewheeling diode, then inductor, then capacitor, and the resistor. So these things we are having, and to make any of the converter, like to make this buck converter, we need these parameter values. So to calculate these value, what we can do is that there can be two modes. When first mode is when the switch is on, and the second mode is when the switch is off. So if the switch S1 is on, in that case what will happen? It will allow the current to pass through the circuit. Okay, so when this S1 is closed, the current will flow in the circuit. Okay, and due to this current, what will happen? The inductor will store the energy in the form of magnetic field, and after that, what will happen? It will discharge in a second mode through the capacitor and the load as well. So we will see that how this is. See, if see, this one is a first mode. When this first mode is there, so this S1 is closed, and that this VL is the voltage across the inductor, and the VC is the voltage across the capacitor. So in that way, we do some KVL calculation, or we apply the KVL in this circuit, and we calculate the formula, which is the basic formula that we want. Okay, and the formula. So this one is a mode 2, where S1 is a open circuit. Okay, so in that case, this inductor will discharge through this capacitor and the resistor. So for that, we need some formula. So I have mentioned here some of the formula there, which is important, which are importance to calculate the inductor value as well as the capacitor value. So here, if you will see in that buck converter, the inductor value is calculated by this formula: L is equal to dVs bracket 1 minus T divided by F delta IL. And similarly, this C is also calculated with respect to the duty cycle and this output voltage. So here we have mentioned that delta IL and delta V naught. So how we will find that what will be the delta IL? So the delta IL will be the 2% of the output current. If your output current is 3, then accordingly you can take this 2% of the output current. Similarly, in this, if you want to calculate this delta V naught, okay, so if you want to calculate this delta V naught, then what you can do is you just take the 0.5% of the V output, okay, output voltage. Now we will see directly to the MATLAB. Okay, so this one is the circuitry, I will explain that how I just designed this circuit in the MATLAB. So if you will see here, I have mentioned the component which are used in the buck converter. The first component here, if you can see, that one is a DC voltage source, okay, and this one is a MOSFET, which is working here as a switch. The I MOSFET to measure the current across the MOSFET and the current across the diode, so that we have connected across this bus, okay, to take the output in the scope. Or what you can do is one more thing. You can directly just connect a scope here, and you can take the output. So how I just take these things, okay. So first, what is the basic thing? Just okay. So how you are going to model these things? The first thing is you just take all the means what to say, this all this component you first take in the screen, okay. Then how you can take, the first method is you just double click on the screen, so the search block will be there. What you do, you just search the component name like MOSFET. You will, so this MOSFET will come. Then what you need, then you need diode. So you just connect this, so you will get the diode, okay. Then what you need, you need one constant block. So just type the constant, so you will get the constant, okay. Now we need a PWM generator, so that PWM generator will come here, okay. So what type of PWM generator we need? We need DC to DC PWM generator, okay. So we will take that one. And why we need this PWM generator? Because we want to switch off and switch on this MOSFET switch. We want that MOSFET operation as a switch to work. This MOSFET to work as a switch, we need some pulse, trigger pulse. For that, we are using this PWM generator. And some other things are there, like DC voltage source, okay. Okay. So you will get the DC voltage source. Then again, if you will just type the R load or R branch, RLC branch, okay, series RLC branch, okay. So you will get this. And in this series RLC branch, if you want to make it just a resistive load, then just take the R. So it will be a resistance only, okay. So you just resistance, and what will happen? Now again, you just type the RLC branch, series RLC branch, okay. Then again it will come. Then here you want RL, so just select and take the this, okay. So you just first arrange these to rotate these blocks. You just press Control R, so this block will rotate, okay, like this, okay. Now you also want one more thing. Here you want one. So you do one thing, copy paste, okay. So you just do this copy paste, so you will get another branch and make it as a capacitive branch. Fine, okay. Now rotate this, so this will come like that, okay. This will come like that, and this will come like that, and this will be here, and this will come here. So you first arrange these things in that way. Okay. Now just do all the connections. You just do all the connections like you want. Okay, like your circuit is looking like. So you just place these connections, okay, like this. You just, yes. So what will happen when it is not connected? It will show dotted red line. When it will connect, it will be a solid black line. So just make sure that it is connected or not. Okay. And yes, so it is connected now. Now connect this one also. This one. Similarly, you can connect in this way. Give the gate pulse and give this. Now the circuit is correct. Okay, fine. Here you can use directly scope also. Okay, if you want to see, and you can connect a scope here and just copy, paste. Again, one scope will come. You just connect a scope here. Okay, and if you want to connect the voltage across the load, then just take the voltage source, voltage sensor actually. Okay, so SIMULINK block. We cannot connect the SIMULINK block in this, so we want this SIMULINK block. Okay, so we will use, again it is coming, so we have to go through this library block, or we can do one more thing. Okay, so if we will go library, I will search here voltage sensor. Okay, so mistake is there, I think. No issue. Voltage sensor. Yes, so you will get the voltage sensor. Okay, so add there this voltage sensor. So now just see here, if this is a buck converter, that I have shown some formula for the output voltage I have mentioned here. That one is V out is equal to duty cycle into V in. Okay, V in means input voltage. So here in this circuit, if you will see, the voltage input voltage is 200 and the output voltage is 150. So if you will calculate the duty cycle by putting these value, then you will get the this duty cycle as a 0.75. So that 0.75 you need to give here. Okay, so I'm just disconnecting this one and I'm giving a constant block. Okay, so like that. Okay, now just give the duty cycle here 0.75. Correct. Okay, now see here again, you have given this duty cycle 0.75 and this one is a PWM generator. Here the switching frequency you can vary up to 5, means the basic thing is that we take the frequency from 20 kilohertz to 100 kilohertz. Okay, so in between any of the frequency, switching frequency you can take, or to calculate the switching frequency we need to know the inductor value. Okay, but in practical case the frequency range is in kilohertz range, so you just take any of the frequency range. Okay, that in this circuit we have taken 10 to the power 3. Okay, now let's see here what is the R value. Here the resistance of this branch is 0.02 and the inductance, whatever formula they are mentioned, we calculated this formula from there only and we got the inductance value is 3 e to the power minus 3. Okay, then the capacitor value which we have calculated, that is 30 e to the power minus 6. Okay. Here every value is mentioned and this one is a diode, so that we have not changed anything here, and we have taken this resistance value as a 10 ohm. Okay, so and this one is a DC source which we have taken as a 200 volt. Okay, Now what we will do, we will run this model and we will check whether it is correct, it is giving output or not. Okay, so I'm just giving here just increasing this simulation time, so it will give you a proper waveform so that you can see here. Okay, so I think this one is a visible screen. Okay, if you will see here, it is going to start and it is going to be slightly higher than 150, and after some time it is going to be settled down at a 150. So what was the input voltage? It was 200. And what is the output voltage we have decided? We want 150. So correct, it is a 150. So just notice one more thing, and this one is a MOSFET current, if you will see here. So this one is a pulsative thing which we have given to turn on and turn off the MOSFET. Okay, and if you will check this diode also, so here also this the current waveform is following the same pattern like a switching frequency, means this switching current across this MOSFET. Okay, so this one is working fine. Accordingly, you can design any of the buck converter just by calculating this inductor value and this capacitor value. That is very important. Okay, and this duty cycle. Okay, so now again I want to show you on yes. So I have mentioned here on another type of converter, which is this one is a boost converter. So just notice this circuit again. We have inductor, switch, diode, capacitor, load, and the DC source. These things we are having. So for that, what we do again, we will do the same thing like we have just tried here also. Okay, okay. So we will just what we will do, we will again, we can take the again MOSFET, then diode. You need to be clear that which diode you are connecting. So you just check that. Okay. So because you cannot connect semi escape block and Simulink block directly. Okay. So just be sure this black color is showing that this is a Simulink block, and this blue color is showing that it's a semi escape block. So don't make any confusion here. Okay. And then again we will type like that, so we will get all the components again. In the similar way, you just connect those things again, and you will just form the circuit, this one. Okay, and here the most important thing is this formula. Whatever the formula like we used in buck converter, here we are using a different formula. The formula is V output is equal to V input divided by 1 minus D. Okay, so here, what is the meaning of boost converter? That means we want to increase the input voltage with respect to the, if we are just if we are looking at the output voltage. So what we are doing, we are increasing the output voltage with respect to the input voltage. So in this circuit, we have used this V input as a 24 volt, and in output we are using it as a 48 volt. For that, we did calculations and we got the duty cycle as a 0.5. So you need to give, and in that case, we have just giving the frequency slightly higher than this buck converter. Okay, you can take the 10 to the power 3 also, there is no issue. But for the proper waveform, okay, we just adjust this switching frequency according to the output waveform. So here we have taken 20 e to the power 3. Okay, and in this RL again we have taken the resistance value 1 e to the power minus 3, and this inductance value is 250 e to the power minus 6. Okay, so how we have calculated these things? These things we have calculated from the formula again we have calculated the formula, and you will get the formula here. Okay, so you calculated these things again by this formula. Okay, whatever the L and R value we are having, you can calculate this from here also. Okay, because delta IL, you know how to decide. It's 2% of the output current. Delta VC, you know, and you can calculate from here C and L. You can also calculate C and L from here. Okay, so now if you will go here again, so we have taken this L value as a 250 to the power minus 6, and the capacitor value we have taken here as a 200 e to the power minus 6. Okay, now, and what is the this load value? This one is a 3 ohm, as a we are considering as a load value. So we will run this and we will see that this boost converter is running fine or not. Okay, yes, see here. So whatever the output what we want, it is means, if you will see here, it is going to be 60, and going to be after some time it will be a constant DC which we want in the output side. Okay, so this one we want as a 48 volt. If you want to check, you can check here, like okay, so if you will see here, the median is a 4.6, almost it's a 46.86. Okay, because of some ripple it is taking as a median value, but it is more closer to the 48. Okay, so definitely we are getting this 48 volt from the output side. Okay, so that this one is a boost converter modeling that we are going to run, and just these modelings are, if you want to do these modeling, first try to take all the components in a single screen, and after that do the all the connections. After the connections, just give the input parameters one by one. Like here we have connected all the components, and after the connection we are giving the input value of this duty cycle, PWM, MOSFET, and every component we are giving the output. So okay, it's more related to the buck converter and the boost converter, and I hope that you will learn from this, the converter and the boost converter, and try to simulate the same model first, and after that you can change the value of the input voltage and the output voltage for any of the application, and accordingly you just calculate the L value, R value, and the C value. After calculating these value, put these value according to your input voltage and output voltage. Okay, it is not a fixed value, it depends on the input and the output value of your application. So depending on your the application, you can change the L value and the C value. And how you will change? You will change by calculating these L value and the C value from the formula. Okay, so yeah, it's I think this one is a clear view that I'm giving you is a buck converter. This one is a buck converter. Okay, the important thing is that the output voltage formula and the inductor and the capacitor value, because if your inductor and the capacitor value will not be accurate, this will not going to give you the desired output current, okay, or desired output voltage. So these calculations are very important, that you need to have this idea about the calculation. Okay, you can follow any of the book to this buck converter on the boost converter. Okay, for different types of example you will get there. Okay, to practice these converters, and that will be very helpful to all of you. Okay, okay, so thank you very much for paying this attention to this, and hopefully this session you will learn this, how this buck converter and then boost converters are important to all of you. Thank you so much, and yeah, take care.